E is false. And C is false. You see it do that? Yeah, let's wait. Okay, so you take what they give you.
Alright, let's pause and see what you've done in number 1. You'll have a little bit of time if you haven't yet started number 2. Remember, we're just going to do a little bit, talk about it, a little bit, talk about it. Which of the following statement is false? I would not check letter A before you check letter C. Why am I saying that? How do you check a piecewise function for continuity? Remember? It's like number 7 on the AP, the one I gave you. You could graph it, I suppose, in the sense of you could go ahead and put the point 0, 0, right?
Or check one side of limits.
And then
Test the separator.
yeah, I would say test the separator. But if you were to graph it, just because some of you this might make sense, wouldn't this one be better written negative x plus 1? Why did I do that? Y equals mx plus b. So the b is going to be positive 1, which is up here. Now, it doesn't equal, but doesn't it go all the way up to that, just not including? And then the slope would be down 1, right 1. That's my graph. Is it continuous? No. But, Angela, you said test the separator. How can you do this without actually graphing? But you can graph. Some of you, if you can't get the separator thing down, this is another way. But what do you mean by that?
Well, for it to, like, so for the graph to, like, match up perfectly, they have to equal each other at the separator,
Which
which
is
is 0.
Good. And how do you check that?
Well,
One side of it.
Yeah, one side of the limit. You say the limit as x goes, well,
0.
0 from the left.
can you come towards 0 from the left though? No. So we'll say, since there is no left, we'll say f of 0 has to equal, which is the first one, the limit as x goes to 0 from above f of x. And how do you actually do that? What's going on at 0, Angela?
Is that an x equals 0?
Uh-huh.
So it's just 0.
So the function is 0, x equals 0. And then what's going on as I come towards 0 for this one?
It's the same thing.
Does that make sense? So you plug in
Oh,
0
yeah,
to the
yeah.
top, it is 0. Plug in 0 to the bottom, what's 1 minus 0? Oh, is 0 equal 1? No way, Jose. Which means, is it continuous? Oh my goodness. Did I just find the right answer? I didn't need to. Struggle. It's not continuous, so see. But where is it not continuous at? 0. And this is including 0. Now the differentiability thing, just because you guys had AP number 1 with number 7, how would you check whether or not it's differentiable on the open interval? Remember, 0 is not a problem anymore for this step. Yeah. Find the derivative of the piecewise function. But 0 is not a problem because it doesn't say including 0, right? So then if you were to check differentiability, you would take the derivative of the piecewise, piece by piece. What's the derivative of 0? 0. What's the derivative of negative x? Negative 1. However, here's the thing. If it says not including 0, am I even looking at this part? I'm just looking at that part and saying, oh, hey, all the derivatives are negative 1. It is differential. Okay. Anyway, you guys could have kept on checking, but that's letter C. Let's go ahead and take 60 seconds, literally, to see if you could start number 82 if you have not yet. Ready, set, go. You have not yet started number 82. Take a minute to see how you would start. Just by the wording of the question, you can tell MBT applies, right? There's no option that says it doesn't. No, so there's no option that says it doesn't, so you don't have to worry about the continuous check or not, differential check or not. Doesn't matter. Just go straight to conclusion. They're saying find C, and there must be one.
Yes, you understand. Differentiability. Did you find the derivative of this? Let me derivative of
Do you guys ready to go? What's the conclusion of MVT?
what do you guys see?
Well, the hypotheses are if a function is continuous on a closed interval A to B, differentiable on the open interval A to B, then there must be at least one x equals c within A to B such that, what's the box? What's the conclusion? We're going straight there. The average slope equals the instantaneous slope. Hence, in this problem,
F prime
f prime of c is equal to f of
two
Minus
B.
f of b, good, minus f of a, all over b minus a. Remember, think about this being like an average rate of change. You want the latter minus the initial. Final minus initial. F prime of c. Some of you might still be a little confused on this because we've talked through it. Quite a few of us have. Who is f prime of c? The derivative. And do I really need to put a c? No, because a c is just the special x where it's true. So forget it. Just leave x in there and solve for the special x and use c. Equals. F of 2, plug it in. 2 cubed is 8. 8 minus 8 is what? 0? Oh my goodness. F of 0, what is it? 0? All over 2 minus 0. So we're just finding when 3x squared minus 4 is just equal to 0, which is add the 4, divide by the 3, plus or minus square root. Wait. Plus or minus square root?
But you can only have positive.
Oh, so I have x is equal to plus or minus square root of 4 over 3, which is the exact same thing as, they're not going to leave the 4 under there.
2 over square root of 3. Plus or minus.
Aww. Well, number 1, none of them have plus or minus, and number 2, none of them look just like that. I can rationalize, right? That makes it look like D, but where's the plus or minus? It's only between 0 and 2, or the interior, so then I'll do minus. You're good. Okay. And then number 83, how many of you guys have already at least peeked at it? Okay, let's do 30 more seconds. Just to see if you can start. Those of you guys that finished it, just double check and make sure that you're solid, you're good. They didn't trick you. We're asking which ones do not. Who has one they can narrow down and say, well, that's not the answer? Not the answer? Could be the answer. That's not helpful. Can anybody narrow down one and say what's not the answer?
C.
Not C? How come? Wait, but C is discontinuous, but where?
3 isn't on the interval.
Yeah, right? X cannot equal 3, but that's not a problem in between -1 and 1. And even if you take the derivative of bottom to top, all minus top to bottom, all over bottom squared, what's still the discontinuity even of the derivative? It's still just non-differentiable at 3. So therefore, yeah, that's not a problem. Anything else? D. Where is the discontinuous for D? Well, X is for the domain greater than or equal to -1, right? Because that has to be greater than or equal to 0. But that's fine. -1 to 1 is greater than or equal to -1, so it's continuous. Right? And then differentiable, you would say the derivative, p prime of x, is equal to 1 over 2 square root of x plus 1 times u prime. But where's my discontinuity of my derivative? X cannot equal -1. However, do you remember where mean value theorem, how it splits up? It's continuous on the closed interval. And what's going on with differentiable? Yeah, differentiable on the open interval. -1 to 1. Well, if the problem's at -1, I don't care. -1 doesn't matter. So if continuous is differentiable, D is not an option. So now we're in between A and B, and most of you probably say, I don't like B, let me try A, and hopefully he's the answer, right? Most of you probably started there. Question, can I plug in everything -1 to 1 into the original function? Yeah, see, it's continuous, right? Differentiable, what's the derivative of f? Bring down to 1/5. Oh, I said negative, and it's in the denominator, sorry. Of x to the 4/5. The negative puts it in the denominator. Uh-oh. This one doesn't work. The derivative doesn't work where? And zeros in between. So therefore, yep, he's not differentiable. Differentiable does not work, continuous does. All right, cool kids. That was a quick recap of NVT.
There's functions.
There's always only one answer. Unless it was something like the AP where it's like 1 and 2, 1 and 3, 2 and 3. Just ones. Those ones, but those will be explicit in the sense of the answer. Sorry. Oh, which of the following? I guess you're right. It could have been more than one, in like just a normal question, but no, just one. All right, cool kids. Notes down. Notes down. But keep your spirals. Sorry. Keep your spirals open. We're gonna do a discovery to get into the section 3.3.
I'm not even.
Yeah. Just because some of you guys would be like, but I want a title and I want this and I want that, and then it's more complicated. So it's better if you should discover this. You should have your graphing calculators out, hopefully. And go ahead and make sure you're in function mode. Obviously, you should be in radians, even though it doesn't make a huge difference. And be in your y equals. So we're going to graph just a couple things. We're in the back of our spirals, discovery section 3.3, or section 3.3 discovery. You guys should be delineating each of the things we do.
When you take the derivative of oxygen, you have to see if you got that like a pyramid, right?
But if you're just dealing with, it's all we've been doing. You have to do something like we did last year, how you set x equal to t and then y equals the equation in terms of x. Or you have to get y by itself. There's another way. But yeah, you could do it. My relationship looks weird, but the question that we're going to be answering in the discovery. Can you see the relationship between the behavior of the graph of f and the signs and sign changes of the first derivatives? We haven't really talked this chapter yet about behavior. We kind of have. But we've talked about certain isolated points and certain characteristics that are true there, like horizontal tangent lines always occur at zeros of the first derivative. Vertical tangent lines or sharp points always occur at DNEs of the first derivative. Those are called critical numbers or critical points, right? We talked about relative extrema, absolute extrema, how they can happen at the relative ones, which are in the interior critical numbers, or on the endpoints. We've talked about certain characteristics, but we haven't really talked about behavior until now. But the nice thing is we talked about it last year too, just we couldn't do very much. We kind of do a few things if they give us a graph. And so today we're going to start with graphs, and then we're going to wean you off of the graphs and say you don't actually need the graph. All you need is the function because you know some calculus. Let's start, though, with having graphs. Let me quickly talk through the directions and what I want you to do for just 2 problems, okay? And I've given you exactly what I want you to fill in. The first thing I want you to do for each of these functions that's given is graph the function. Literally, just put it in your graphing calculator. I mean, hopefully you could do this one without your graphing calculator, but that one gets a little bit harder. So first of all, graph the function. Sketch it. Using the graph and your calculator to help you with certain points, identify the intervals for which the function is increasing or decreasing. So right here, increasing interval. What? Interval notation. You guys remember from last year? How do you write interval notation? Yeah, x is an element of, and then you use either a parenthesis or a bracket if it's including, parenthesis if it's excluding, so a bracket if it's closed, a parenthesis if it's open. And the nice thing is I'm going to actually help you guys out. all of these, even in homework it says on the open interval. We're keeping them all open, and we did last year too. We talked about increasing, decreasing. However, there might possibly, no, this one. There might possibly, for a given function, be more than one place. But for parabolas, we're only doing one. And then, how do we fill in the intervals? How far left goes first, the first number of the x value, to how far right of the x values. Anyway, filling in interval notation for where the function is increasing and or decreasing. And then I want you to go ahead and find f prime and check the sign of f prime in each of these intervals and tell me what the sign is. You might be able just to look at the graph and figure out from the slopes of the tangent lines, or you might actually find the derivative and do it analytically, we would say, or algebraically. So, ready, set, and go. Shouldn't take you super long. You're getting a sketch of the graph. You're thinking about last year. Increasing and decreasing, that's right. As you go from left to right, it goes up, it goes down. Fill in as much of that information as you can. First function, in case it got too small, x squared minus 3. Second function, x to the 4th minus 2x squared. I'll make it a little bit bigger in case that'll help. You got it? If you don't have a calculator, peek at someone's calculator in your group. Or just realize number 1 is a parabola that's been vertically shifted down 3. In case that helps. Feel free, you can collaborate a little bit. I'll fill in number 1 in just a second. You guys try to beat me. And if you do, go to number 2. How's the first one look? Remember, just like we read a book, we always go from left to right, at least in English anyway. We go from left to right. That's the common way of looking at a graph. And you're asking yourself the question, what are the heights doing? What are the y's doing? Are they falling or are they rising? So as you go from left to right, this graph is falling up until it hits when x is 0.
Oh, is that by the y?
Remember? The y's, the increasing, decreasing describes what the y's are doing that we're saying for which x's. So we're using both.
Oh.
So from negative infinity all the way till x equals 0, the y's are falling or decreasing. And then the y's start increasing as x goes from 0 to infinity. Now, why do I have negative and positive down here for the sign of f prime?
The sign of the slope.
The sign of the slope. All the slopes from negative infinity up to 0, not including 0, which might help you out as to why when you have an open interval. All the slopes are negative up until 0. And the slope is 0. And then all the slopes are positive. How does that correspond to what's up above? A negative derivative resulted in what behavior of the graph? and a positive slope related to what behavior in the graph? Alright, if you guys haven't yet done number 2, let me zoom in on that one. And let's see if maybe this pattern continues. Remember, I'm allowing you to graph in your calculator. No way, how did I get that W so fast? And it's actually really precise. No. All the math is right here. What did I do? I found my zeros first, right? And root 2 is a little bit past, negative root 2 is a little bit past negative 1, positive root 2 is a little bit past positive 1. But how did I know exactly where the mins and maxes were? Last year we just guessed and we had to like plot random points and hope we found it. What always happens at mins and maxes? So I found my critical numbers. I figured out 0, positive, and negative 1. The one math thing I didn't show, well, at 0, technically is a multiplicity of 2, so I knew it had to bounce there. Whoa, that was pre-cal. Anyway. And at the other 2, they only have a multiplicity of 1, so it passes through. Yeah, maybe that's cheating. But plug in 0. What's the y value at 0? 0. Oh, I already have that point. Plug in negative 1. What's the y value at negative 1? 1 minus 2 is negative 1. So negative 1, negative 1. At positive 1, same thing. Positive 1, negative 1. I just did a little baby table in my head. I plugged it in, found the y values. And I knew because they were critical numbers, I knew it was a quartic. It had to go boing, 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 boing. Done. Anyway, we're getting there. A question. You guys could have gotten that in your calculator real fast. I'm just showing you the math as to where we're kind of going. But where's this function increasing? Do they know what George has first grade? That's what I was thinking.
Yeah, I think there's no finance.
Okay, coming back. So where's the function increase? You guys started talking. Moving left to right. Negative 1, 2. Good. You remember this fancy math symbol to go ahead and connect separate intervals? U for union. Or, and then it decreases for a bit, and then it starts to increase where? 1, all the way to infinity. I kids I didn't have for pre-count might be a little rough to catch up, but are we doing all right? My pre-count ones are doing all right? Okay, decreasing. Where's it decreasing from? Negative infinity to negative 1. Union. 0. The signs of the slope. What are the slope signs from negative infinity to negative 1? Negative. Oh yeah, negative was decreasing. So where else are the slopes going to be negative? 0 to 1. Good. The slopes are going to be positive. What are the others? So did we discover the relationship between the signs of the derivative and the increasing, decreasing nature of the graph? For the entire interval where a function is decreasing, the slope of the derivative will be negative. For the entire interval where the function is increasing, the slope of the derivative will be positive, etc. Now, notes open. We're going to go to section 3.3. If you guys don't mind just looking up here before I turn the page. Where can a graph change from increasing to decreasing or decreasing to increasing? Critical numbers. Because they theoretically are relative maximums or minimums. Theoretically. And you might see something today if we can get there. Critical numbers aren't the only places a function can change. What? There's another way a function can change from increasing to decreasing? We'll get there. But the most obvious one is critical numbers. Now question, what kinds of critical numbers was this entire page? Zeros or undefined? Zeros, because they were all smooth turns. Question, if there was a sharp turn, would it change from decreasing to increasing also? Ooh, so the zeros or the DNEs. Oh yeah, that's what critical numbers are. That's right. Section 3.3, here we go. Increasing, decreasing, and the first derivative test. Literally, an entire section on increasing, decreasing. Ooh, and the first derivative. This graph you see should look kind of familiar last year, because when we first talked about just increasing, decreasing, we were like, oh yeah, decreasing, as you go left to right, it goes down. Increasing, as you go left to right, it goes up. Constant. Over an interval, not a point. Over an interval, the graph stays the exact same height, aka the slope is 0. Over an interval, not just at one point, but over an interval, the graph stays at one height. And then as you can tell, what you guys discovered and what we were doing, for decreasing nature, the derivative will be negative that entire time. For increasing nature, the derivative will be positive that entire time. Doesn't mean they'll be the same negative number. It's going to be different negative numbers, usually. The function is decreasing. Either negative slopes getting more negative, or negative slopes tending towards 0. And for a constant portion, the derivative is 0. But remember, to be constant, to have a constant interval, the graph has to have an actual interval, a beginning and an end, over multiple points, not just one. Now, down below, some of you guys, maybe this will help seeing an actual definition of increasing and decreasing functions. I don't think we even really wrote the definition of increasing and decreasing last year. Maybe it wasn't even there. But a function is increasing if for any two x's, the first x and the second x is greater than or further to the right than the first x. If his y value is going to be greater than the first y value, if the first y value is going to be less than the next y value, the function must be increasing. And similarly, if you have a latter x and an earlier x, x2 being the one further to the right, if the earlier y value is higher than the later y value, for any two numbers in that interval, then the function must be decreasing. Nice thing is, this is not a forever card. It just gives you a little bit more, rather than just a graphical representation of increasing, decreasing, it also gives you a more analytical, more algebraic way of thinking about it. But once again, not a forever card. It's more of just an understanding. You're like, big deal. I mean, it took a second to remember, oh yeah, that's right, as you move from left to right, and then use the x's to talk about the beginning and end of the increasing, decreasing constant portions. But big deal. With the graph, it's easy, right? So what if I took away the graph? Oh. Well, that's okay. We have the tools that we need. If I take away a graph, how can you still figure out how a function is behaving, moving, changing? Are we almost there? Okay, for sake of time, see how much space you need to skip. function is increasing and or decreasing. Let's see if our idea that functions can only change from increasing to decreasing at critical numbers is correct. Just give me intervals. X is an element of. Might be more than one. Probably is. Where's a place where this graph is increasing?
4 to 5.
4 to 5. I agree. We're approximating, right? 6 to 7. 4, 5, 6. We can say, let's put little arrows, huh? 6 to infinity. Sound good?
Yeah.
Okay, 6 to infinity. Anywhere else? Okay, where's it decreasing?
Negative infinity
To 1. Why are you cutting it at 1? Because there's a vertical asymptote. Okay, now what? Where else is it decreasing? Good. Had to split up at 1. We couldn't go through 1, so it doesn't exist at 1. And then 5. Where did we have to split up these intervals? At critical numbers, yes, right? Here's a sharp point. That would be a d/n(e) of a derivative. That's a smooth turn, a quick smooth turn, but smooth turn. Another sharp point. We have 2 d/n's of derivatives. We have 1 0 of a derivative, and then what was that other place that necessitated our splitting up? Ooh, discontinuities. And so tomorrow we're going to pick up with increasing, decreasing test. When does it start? And then we're leading up to basically a sign chart. Sign charts you saw last year, and we'll get into it. Guys, you already saw that we need a couple days to go through this. Nice thing is, you can work on other homework tonight besides calculus. I wouldn't really even start. And if you want to trick or treat on the way out, you may. Bye, guys. Chapel day. I'll see you later. Even though you're not in costume. Get in costume, go to Chipotle, $3 whatever. Sorry, only chocolate. Let's answer those that can be chocolate.
I was this week was horrible. I had to go
Happy Reformation Day. Thanks, Susie.